let's discuss problem E. We have several exams. This is funny. Greedy and a lot of math. I would say it's a little of math and a lot of greedy. So I disagree with it. Actually, I can remove one of the maths, can't I? Yeah, I can remove one of the maths. Oh, now it... Sorry. Okay. Is it really possible to make a lot of maths? Okay, I broke it. Sorry, guys. Sorry. I really destroyed a lot of maths here. Okay. Never mind. We have an array of integers. And your friend does not like when a GCD of two integers is 1. They just don't like it. And you say, okay, I can take k operations, and during each of them, I can replace some number with 0. I can make at most k such operations, and I want to minimize the number of pairs in which GCD is still 1. And you need to find the number of such pairs. This is kind of greedy problem, but it's greedy in a clever way. So you cannot just go from left to the right and make number zeros. Instead, there is a kind of clever way of making number zeros. So first of all, you should notice that if you replace a number with 0, 3 things can happen. Either, so each number is in 2 pairs, in the left pair and in the right pair. Maybe one of them does not exist if we are considering edge case, but still, at most 2 pairs. And we can either make 2 fixes, or 1 fix, or 0 fix. 2 fixes is, for example, if both these GCDs were 1s and they became non-1s. How could it happen? It could happen if they were both 1s, GCDs, but these numbers were not 1s themselves. Why is it important if a number is 1 or not? Because if you have AI and 0, AI minus first and 0, this pair only depends on this number. Actually, the GCD of these two numbers is the left number. So if it is 0, if it is 1, sorry, then the GCD is also 1. And if it is greater than 1 or 0, so like not 1, then GCD would also be not 1. So it is important if number is 1 or not 1. Okay. Sometimes it is only 1 fix. 0 fixes can happen only if you have 1, some number, and 1. Then if you replace it with 0, nothing changed at all. So to solve this problem, actually, what you need to understand? You need to understand that you need to make as many operations of such type as possible. Then you just need to make as many operations of this type as possible. And operations of this type will be possible until the array is totally fine. For example, it is all zeros, or not, but still but still no pairs of just t equal to 1. So let's look at our array. Notice that if there are two elements which are not relatively prime, they have GCD not 1, then they will be never relatively prime. The only way to make them relatively prime is to... So they have some common divisor p. You should do something to make them not have this divisor p. The only thing you can do with these numbers is to make them zeros, in which case p still divides 0. So you cannot eliminate divisor p. Actually, they will also be a good pair. So having said that, you can just divide your array into parts and solve the problem separately in the left part, in the right part. It's not really true because you have like common k operations and you need to decide whether something goes here and something here, or everything goes to the left part. In this case, in this sense, they are not separate. There's still a common problem. But yet, it is better to consider them like two different like problems, and you just have some budget k which you need to spend to divide them across your problems. Okay, let's do all separations of such kind which we want. And in the end, what we will have is several segments, and in each of them, there are only ones. All pairs are relatively prime. So there are several pairs of relatively prime numbers. Maybe some groups consist of one number, in which case we are not interested. Yeah. Okay, let's think of how each block looks like. It looks like this thing. You have several numbers which are not ones, but still relatively prime numbers. Then you have several ones. Then you again have several numbers which are not ones. Then you have ones, etc. This is, maybe you have only also ones here, but not necessary. And also you can have ones here, but not necessary. This is how your problem looks like. So as I said, we want to preferably make the operations which fix 2 pairs, then fix 1 pair, then fix 0 pairs. So in this particular situation, what fixes 2 pairs? Actually, each of these elements fixes 2 pairs. Each of them. But not everything is so easy, because if you fix some element, it becomes 0. Then you have this separation. And now fixing of this element will not help you with left pair. So yes, all these elements now fix 2 pairs. But you cannot take all of them. You can take like half of them. So in general, if you have a block of k numbers which are not ones, you can take like k minus 1 over 2 of them. And they can be independent 2s of this type. So this is our first priority, actually. We take all such blocks. In each of them, we take all 2s. So like every second element, starting with not at the end one. Sorry. Okay, what is the second priority? Actually, there are some sort of elements which there are some types of elements which are not fixing two pairs, but after some operations they can fix two elements. What I'm talking about is ones. Yeah, consider these three ones: 1, 1, 1, 5, and maybe 6 here. At the moment, none of them fixes two elements. For example, this element if you replace it with 0, only this pair is fixed, but this is not fixed. Yeah, so this fixes one element. After that, this fixes one element, one pair. But now this element fixes two pairs, this and this. So there is like potential of ones which can fix two elements at one moment. So actually, if you work with ones one by one, then each of them gives you +1 to your answer. But last of them will give you +2 to the answer. Okay? And actually, this only works for ones. Yeah? For example, if you have some regular number like 5, yeah? If you have 0 here, then it is already a good pair. So it cannot be like fixing two pairs at the same time. Ones is the only place where we can get this resource from. So actually, what you need after such blocks is take some block of 1 and fully eliminate it. But what block to choose? This is an interesting question. What you would like to do is to end a block, yeah? Because when you end a block, you get this +2 instead of +1. This means that you want to kill as many blocks as possible. And this means that you need to start with the smallest blocks. Yeah? So let's sort. Let's find all blocks of ones, sort them in increasing order, and eliminate each of them from one end to the other end. Not really important in which order. From one end to the other end. There is a corner case. Sometimes there are several ones which are attached to the left end of the array or to the right end of the array. Why is it a corner case? So suppose you have like 1, 1, 1, 6. Then each of them gives you +1. You could say, what about in the other order? Yes, in the other order, in the end, this will give you +2. But only because this one gave you +0. Yeah, this simply did not fix any pair if you start with the left. So these ones, they definitely give you +1s, but not +2. So they are not participating in this sorting. If there are such blocks, you consider them at the end. Okay? So now we have the following algorithm. It is greedy, but still it's like complex greedy. First of all, we consider non-one blocks. And you take b over 2 elements. b minus 1 over 2 elements from it. Then you take 1 blocks not touching the border. So we sort in increasing order and destroy one by one. Okay, what about blocks which touch the border? Actually, if we destroyed parts 1 and part 2, so these two parts, if we have done them, then we will never get +2. We will never get +2. Why? Because actually you can't. Well, you can, but only if you have this block of ones touching the order and you started with +0. And there is no need to start with +0 if you can do it from right to left and always get +1. So if you forbid operations which do +0, and there is... you know what I mean. I mean, we forbid to get +2 only, which is only caused by getting 0 in the beginning. This is what I mean. If you do it, actually, the rational way to order is from right to left. You cannot get greater than +I for I once. So, the third part is 1 blocks which touch the order, the border. We destroy them from the center to the edge. Okay, I mean from one edge of the block to the other block of the... from one edge of the block to the other edge of the block. But if one of the edges is touching the border, then you definitely need to start with the other one of them. And finally, just what makes sense. What do I mean by that? We just traverse through all elements from left to right, and if you see that element has GCD with one of them 1, you need to replace it with 0. That's it. You can't do anything better because, well, as I proved before, you cannot get +2 anymore. You can get +2 only with ones, and all ones are by this moment eliminated. So I think it's a good idea to show you my solution. So first of all, I consider all blocks which consist of non-ones, but GCD are ones. In this case, I take this element and set it to 0, and I decrease k. Actually, I allowed it to be like 1, not 1, then 1, then not 1. Yeah, so I didn't check that vi is 1, is not 1. But this is fine. So this is like first part. Then I find all blocks of ones. This is the function which finds all blocks of ones. This is straightforward linear algorithm. Then I sort these blocks of ones by the following, with the following comparator. If none of them touches the border, then I take that of them which is shorter. If one of them touches and the other one does not touch, I choose the one which does not touch. And if both touch, then I again just take minimum size. Actually, you can take anything if both touch the border. When I have all this sorted, I take each of them and go from one edge to the other edge. And if one of them touches the border, I start with the other edge. I again 0 it y by 1, and each time I decrease k. Finally, I do what makes the most sense. This is this part. Here I look at the element, and if it has GCD 1 with either left neighbor or right neighbor, I make it 0. Okay? Actually, you could, during all of this process, maintain your answer. Yeah, for example, this also always gives you +2. This always gives you +2. Here it always gives you size of block +1. It always gives you size of block. Also, there is some sort of course, corner case when all elements are ones. I think you should consider it separately. Yeah, because in this case you will get b minus 1, where b is the number of operations you spent. Yeah, but usually the number of operations you spend is the number of points you achieve. So b plus 1 if destroyed block, and b if not destroyed. Okay, and finally what makes sense is just +1 each time. So I could maintain it during the solution, but I thought it would be nicer to just make them zeros, the element that I want. And in the end, I just calculate the answer from scratch. I consider all pairs in which GCD is 1 and add 1 to ans for each such pair. This because it is a bit slower, but still it minimizes the probability of error, which I do not want. Okay, that's my solution. And I do not agree that there is a lot of math. Maybe in some future contests you will see a problem with a lot of math, but it is not. You just have like n or n half or n half plus 1, something like this. It's not a hugely math problem.